Okay, so, like, picture this. We're trying to build a computer, but not just any computer, one that actually works like the human brain.
Yeah. That's the big challenge of neuromorphic computing is what we're going to be looking at today.
Exactly. And the amazing thing is this isn't just like some sci-fi fantasy.
Yeah.
We actually have neuromorphic chips out there.
Yeah.
You know, they're doing real work.
It's pretty different from how computers work now.
Right, totally.
I mean, we're talking about like mimicking the brain's structure with artificial neurons and synapses.
Right, and we're going to talk more about the details of how that works, but it is happening. And Jörg-Owe, he's a researcher who's been kind of mapping out this whole field.
He has, yeah.
He has this roadmap, and it talks about both the potential and the challenges.
Yeah, it's exciting stuff.
Yeah.
I think what's really fascinating is it could like completely change how we think about AI. You know, like imagine AI that's not only faster and more efficient, but can like solve problems that traditional computers just can't handle. Like
self-driving cars.
Right.
That can make split-second decisions. Or robots that can learn like humans.
Yeah.
Even hearing aids that can like filter out all that noise.
Right.
Make it crystal clear when you're having a conversation.
Absolutely. I mean, we're like at the beginning of a whole new era of computing, I think.
Yeah, and the thing that blows my mind is this journey actually started a while back.
It did.
Back in the 80s.
Yeah.
Carver Mead.
Professor at Caltech?
Yeah.
Yeah, he came up with the term neuromorphic and actually built the first silicon retina and cochlea based on the way our eyes and ears work.
I know. Like, nature has already solved so many of the problems that we're trying to tackle with technology. It's incredible.
Oh, God.
And then there was that huge human brain project in Europe.
Yeah.
To simulate a whole human brain on a computer.
Ambitious, right.
Super ambitious.
That's a great example of how thinking big can push the limits of what's possible. And we've seen some incredible things happen, like IBM's True North chip.
Right. With 1 million artificial neurons.
Yeah. Super energy efficient.
And then Intel's Loihi chip, which can actually learn and adapt in real time.
Yeah. Just like a biological brain.
Amazing.
I mean, these aren't just ideas.
Right.
These are real chips doing real work.
So we've got these like brain-inspired chips, but how do they actually work?
Well, okay, so think about this.
Yeah.
In a traditional computer, the processing and the memory are separate. It's like having this library where you've got to go back and forth between the reading room and the stacks to get the information.
Okay.
But in the brain, it's all happening together constantly.
So these new chips, these neuromorphic chips, they're designed so that the processing and the memory are right next to each other.
Exactly.
Like in a brain.
Like in the brain. Yeah, that's one of the key principles.
Genius.
Integrating processing and memory for incredible efficiency.
It's like having all the books right there at your desk.
Exactly.
No more running back and forth. But there's more to it than just location though, right?
Yeah, absolutely. It's about how information is processed as well.
Okay.
Traditional computers work on a clock cycle, constantly crunching numbers. But neuromorphic computers are event-driven.
Okay.
They only process information when there's a change.
I see.
Like our neurons. They only fire when they're stimulated.
So it's more like a light switch.
Exactly.
On or off.
Yep.
No wasted energy on things that haven't changed.
Exactly. That's a brilliant way to save power.
That's so cool.
And this event-driven approach is really well suited for something called spiking neural networks, or SNNs.
SNNs.
Think of it like a network of fireflies. They only flash when they get a signal.
Okay.
And that's kind of how neurons in an SNN communicate. And that makes them super energy efficient.
So we're recreating the brain's elegance and efficiency in these chips.
We are, yeah. We are.
Jörg-Owe, he really emphasizes this.
He does.
Doing more with less.
Yeah.
And it's really interesting because it's inspired by such a complex system.
Yeah.
Like you need expertise from so many different fields. You've got material scientists developing the new materials for these chips.
Right.
You've got engineers designing the circuits.
Yeah.
And then algorithm developers figuring out how to program them.
Absolutely.
It's a real interdisciplinary thing.
Yeah, just like understanding the brain itself.
It's like we're trying to unlock the secrets of the most sophisticated machine that we know.
We are.
So how do we go about building these neuromorphic systems? Are there different approaches?
There are, yeah. It's like picking the right tool for the job.
Okay.
You've got digital architectures, ones and zeros, like a precise scalpel, right?
Right.
Ideal for tasks that need accuracy.
Got it.
And then you have analog architectures, which are more like,
Okay.
a flowing river, continuous signals. They're super energy efficient and good at real-time processing.
So digital's about precision.
Yeah.
And analog is about flow.
Yeah, exactly.
I like that.
And then you've got the mixed signal architectures, which combine the best of both.
So it's like having all these different Lego blocks to build your brain-inspired computer.
Exactly. Yeah, and the research is always evolving, to make these systems even more brain-like, trying to recreate the brain's connectivity and organization, basically building mini brains on chips.
Okay, but I'm sure people listening are like, yeah, this is all cool, but like, what can it actually do? Let's talk about the applications.
Let's do it.
The stuff that could actually like change lives.
Okay, so get ready for some seriously exciting stuff.
Okay.
Let's start with robotics. Imagine robots that can learn by doing and can adapt to new environments and make decisions in real time without needing to be reprogrammed all the time.
So like they can think on their feet.
Yeah, exactly. Just like humans do.
And because these chips are so energy efficient,
yes,
we could have robots that can run for a lot longer.
A lot longer, yeah.
Without being plugged in.
Without being tethered to a power source.
Amazing.
Exactly. And we're not just talking about like factory robots,
Right.
We're talking about robots that, can do search and rescue or can help with surgery, reacting to changes in a patient's condition, it's...
Sounds like a sci-fi movie.
It does, doesn't it? But it's real. But it's not just about, the big stuff.
Yeah.
There's potential for everyday life too,
Right. Like hearing aids.
Yeah, exactly.
Like the ones we were talking about before.
So current hearing aids,
Yeah.
they can amplify sound.
Right.
But they have a hard time in noisy environments.
Yeah.
Can't tell the difference between, speech and all the background noise.
Right.
Neuromorphic hearing aids, that changes everything.
So because they process sound more like the brain does,
yes,
they can actually like filter out the noise.
Filter out the noise.
Even in a crowded restaurant or on a busy street.
Absolutely.
Wow.
And that can totally change the quality of life for people who have hearing loss.
Yeah.
It's all thanks to the fact that these chips can process information in real time.
Like having a tiny brain in your ear?
Like having a tiny brain in your ear, making sense of all the sounds.
That's incredible. What about edge computing?
Oh, yeah.
This is bringing the computation closer to where the data is generated.
Exactly.
Like our smart homes, self-driving cars, or, wearable medical devices.
Yeah, so traditionally, all that data is sent to the cloud.
Right, process.
Right, at time.
Takes energy.
It takes time, takes energy, yeah. But with these chips, we can do a lot of that processing right there on the device.
Instantly.
And
that makes it more secure, too.
More secure, yeah. More private. Because the data is not being sent to a remote server.
And Jörg-Owe, he lays out all these possibilities in his roadmap. It's amazing. Like a future where this is everywhere.
Yeah.
Towering everything. Mm-hmm. From our homes to our cars to healthcare.
Absolutely. I think so. I think it's a future where AI becomes more part of our lives.
Yeah.
But in a way that feels more natural, more human.
Right. But we should also talk about the challenges.
Yeah, of course. It's not all easy.
Yeah.
And Jörg-Owe, he's very upfront about this in his work. This is not simple.
Right.
So, for example, finding the right materials for these chips is a big deal.
It's not just silicon anymore.
No. We need materials that act like neurons and synapses. And that's a whole area of research in itself.
This is like needing the right building blocks.
Yeah, you need the right building blocks. And then there's the issue of scaling up. I mean, we've got True North and Loihi.
Yeah.
But they're still pretty small compared to the human brain.
Right. It's like, it's one thing to build a model airplane, but it's a whole other thing to build a real one.
Totally. Yeah. And then there's the whole software side of things, the algorithms.
Right.
Like, how do you program these computers? We need new ways of thinking about programming, ways to really use the power of these chips.
It's not like you just give it a set of instructions.
No.
Like step by step. It's got to learn and adapt.
Exactly. It's got to be able to learn and adapt on its own. Yeah.
Wow.
It's more like training a dog than programming a robot.
I like that. And we can't forget about sustainability.
Of course not. Yeah.
All of this needs to be done in a way that's good for the planet.
Absolutely. And that's something that Jörg-Owe really emphasizes,
Right.
We've got to find sustainable materials.
Yeah.
Energy efficient processes.
Right.
And create systems that don't add to our environmental problems.
So it's not just about technological advancement, but making sure that advancement works with the planet and everyone on it.
Absolutely. Yeah.
But let's end on a positive note here.
Yeah.
what are some of the things, the advancements that are giving researchers hope?
Well, I think IBM's True North and Intel's Loihi are great examples of, processing power and energy efficiency. And there are other really cool things happening too.
Like that Halo Point system.
Oh, yeah.
That massive neuromorphic computer built by Intel. It's got over 1 billion artificial neurons.
That's right, yeah. Getting closer to the scale of the human brain.
And it's not just about the hardware. There have also been advancements in algorithms.
Absolutely. Yeah. New ways to train those spiking neural networks, making them more efficient, more capable.
With a lot of momentum.
A lot of momentum, yeah. And that's what's so great. It's not just a few labs doing this anymore. Right. It's a big global community pushing the boundaries of what's possible.
That's exciting.
It's super exciting. It's like we're at the beginning of a whole new era of computing, inspired by the human brain.
And who knows what we'll discover next.
Exactly.
This has been an incredible journey so far, but we're not done yet. We'll be back in just a moment to delve even deeper into the future of this groundbreaking technology. Stay tuned.
Stay tuned! Welcome back to our deep dive into neuromorphic computing.
It's amazing how much we've covered already.
Yeah, it's a lot to take in. We've just started.
It really is. Like, my brain is like rewiring itself just listening to this.
It's exciting though, right?
It is.
I mean, we're really pushing the boundaries of what computers can do.
Totally. And Jörg-Owe, he points this out in his roadmap too. Mm-hmm. We're not just copying the brain's structure anymore. We're starting to understand and replicate its function.
Yeah, it's not just about building artificial neurons and synapses.
Right.
It's about figuring out how the brain learns, how it adapts, how it makes decisions,
And that leads to some really cool stuff with machine learning and AI.
Totally, yeah. Like traditional machine learning, it needs tons of data to learn. But with neuromorphic systems, because they're based on the brain, they can potentially learn from much smaller data sets.
So it's like the difference between cramming for a test and learning gradually over time.
That's a great way to put it.
The neuromorphic system is more like a student who's constantly learning.
Yeah, building on what they already know. And that's really important for things like robotics and self-driving cars, anything that has to interact with the real world.
Because the real world is always changing.
It's unpredictable, yeah. Makes me think of those movies where the robots become so advanced that they start to seem human.
It's like, are we going there?
That's a big question, yeah. And Jörg-Owe, he talks about this a lot in his work too. We are entering uncharted territory, not just with the technology, but ethically and philosophically too.
Right. But for now, let's stick to the practical stuff.
Yeah.
Earlier, we talked about the potential for neuromorphic computing in healthcare. Like, where are we seeing real progress?
Well, brain-computer interfaces.
BCIs.
Yeah, BCIs. They let the brain communicate directly with a computer.
It sounds like science fiction.
I know, right?
But it's happening.
It is happening. They're already being used to help people with paralysis.
Wow.
Control prosthetic limbs, and that's just the beginning.
So you're saying we could bypass damaged nerves?
Yeah.
Or even replace lost sensory input?
Potentially, yeah. With signals from a computer.
That is amazing. And that goes beyond just movement too, right?
Oh, absolutely. Researchers are looking at using BCIs to treat things like epilepsy and Parkinson's. Imagine a device that could detect a seizure before it happens and then deliver a little electrical stimulation to stop it.
That would change so many lives. What about personalized medicine?
Oh, that's another big one.
Like tailored to your brain activity.
Exactly. Because everyone's brain is different. In traditional treatments, they're kind of one size fits all.
Yeah. And that doesn't always work.
It doesn't always work, no. And neuromorphic computing could help us move toward more personalized treatments.
So we've talked healthcare, but what about other fields? Like finance?
Yeah.
Cybersecurity?
Absolutely. There's potential there too. In finance, these systems could be used to spot fraudulent transactions in real time.
Wow.
Or to analyze market trends.
So instead of relying on old data, we could have systems that can learn and adapt to changes as they happen.
That's the idea, yeah. And in cybersecurity, you could have systems that can learn to identify new threats as they pop up.
That would be incredible. It's like having a security system that can think for itself.
Right. Yeah. So it's not just about copying what the brain can do.
Yeah.
It's about using that to solve problems that normal computers can't.
That's what makes this so exciting.
It is. It's like we're at the beginning of something huge.
It's like a technological revolution. And Jörg Schnepat's roadmap is a great guide for all this. He's not just talking about the tech stuff. He's talking about the ethical and societal implications too, which is so important.
Yeah, I agree. Any powerful technology, there's the potential for misuse. And we need to talk about these things now. Not just scientists and engineers, but everyone, really. Philosophers, policymakers, the public.
It's not just about building smarter machines. It's about building a better future for all of us.
Absolutely. And I think it's really good that a lot of the top researchers, like Schneepat, they get this.
Yeah.
They're trying to build safeguards into the technology right from the start.
So it's not just about the what of neuromorphic computing. It's the how and the why, making sure it's used responsibly.
Absolutely.
This has been incredible so far, but we're not done yet. We'll be back in a moment to explore some of the most mind-blowing possibilities, things that might seem like science fiction now, but could be reality tomorrow. Stay tuned.
Stay tuned.
We'll come back to the final part of our deep dive into neuromorphic computing.
It's been quite a journey, from those early silicon retinas to self-driving cars.
Yeah. Now, I want to shift gears a bit, look beyond just the, practical applications.
Oh.
We've talked robots, we've talked healthcare.
Right.
But what about the bigger picture?
Mm-hmm.
What about the stuff that's still kind of like science fiction?
You want to talk about like the really mind-bending stuff?
Yeah.
Well, I think one thing that really gets people excited is like cognitive machines.
Okay.
Machines that don't just process information, but understand it, you know? Machines that can reason, make judgments, maybe even have some kind of consciousness.
Whoa. Okay. Now we're getting really deep here. Is that even possible?
Yeah.
Can we actually make machines that think like humans?
That's the $1 million question. Right. I mean,
Yeah.
that's the question that's been in so many sci-fi stories and philosophical debates. And Jörg-Owe Schneepat, he talks about this in his roadmap.
Yeah.
He says that, neuromorphic computing, it could take us down that path.
Right.
But it brings up so many ethical and philosophical questions.
It really does. It's almost like we're talking about creating a whole new species.
Yeah.
Like a species of intelligent machine.
That could maybe even be smarter than us.
Right. That's exciting and scary all at the same time.
It is. It's awe-inspiring and a little bit daunting, for sure. I think if we're going to create machines that are as intelligent as humans, we have to make sure that they share our values.
Right.
And that they're used for good.
It's like, what if they get into the wrong hands?
Exactly. That's a very real concern. And I think that's why we need to be having these conversations now while it's still early. And it can't just be scientists and engineers,
Right. Yeah.
It's got to be philosophers, ethicists, policymakers, everyone.
It's about how we use this technology.
Yeah.
And what kind of future we want to build.
It is. It's about responsible innovation.
And it's encouraging that a lot of the top researchers, like Schneepat, they get this.
They do, yeah. They're really focused on building safeguards into the technology from the very beginning.
So it's not just about building smarter machines. It's about building machines that are aligned with our values that can help create a better world.
That's exactly it. And I think neuromorphic computing has the potential to do that.
Yeah.
To be a force for good. But we have to be thoughtful and careful.
Absolutely. This has been an incredible journey, exploring this whole world of neuromorphic computing, from the basics to all the potential applications and some stuff that is just mind-blowing. I think it's clear that we're at the very beginning of something big.
We are. We're at the start of a revolution, really.
And Schneepat's roadmap, it gives us a glimpse of that future.
No.
It makes us think about the implications, which is so important. So to everyone listening, keep exploring this, keep asking questions, and imagine the possibilities.
Yeah, because the future, it's what we make it. And with this technology, we have a chance to create a future that's smarter, more sustainable, and ultimately more human.